Thank you very much. It's actually this is the first time I've been to the HPC Advisory Council meeting, so this is new for me, and it's really good. I know coming in, I was kind of wondering, well, what's the crowd going to be like? If I go and talk at ECMWF, it's very technical, and they get down into optimization. They want to talk about bits and bytes and bandwidth, and sometimes when I go to other talks, it's a higher level. We might talk about investments. We might talk about realization of benefits. Talk about how the organization can achieve more through their investments, that return on investments, which is the thing that you have to kind of keep your eye on. If you lose track of it, then you're going to have to start explaining why it wasn't on track, why you weren't able to deliver what you had first set out to deliver. So in the program is very much about that. It's looking at the investment. This is a 7-year program starting in 2014, ending in 2021. And it is to improve the Bureau's weather and forecast services, improving the skill of it through numerical prediction. So we talk about, just the Bureau as a context. It's a 24/7 operational facility for numerical weather prediction. And the basis, the main piece of equipment that enables that is the high-performance computing. Trying to solve those Navier-Stokes equations on a globe, taking into account all the thermodynamics and boundary conditions. And of course, what we'd really like to do is get to a model resolving, convection resolving model, something that's going to be able to very much model everything from fog to convection of thunderstorms to tornadoes to tropical cyclones, you name it, and we're trying to resolve the physics. So when we look at that, we look at our large-scale dynamics, trying to do climate simulations, resolving down to 40 kilometers. We're looking for our global weather models to get down to 1 kilometer. We're looking for our fog modeling and bushfire modeling to get down to 100 meters. So there's a lot of aspiration in that because we're not there today. So in 2016, we put in a system. It went live on the operations. It was one of our first, or I should say second deliverables. The first deliverable was the data center that the system was sitting in, where we chose a data center from a commercial provider in Melbourne, outfitted with all the water cooling and infrastructure needed to run a supercomputer from Cray. And then also investments in the networks between the data centers. So we got the system in there. It was running operationally. It certainly has been a nice change for the Bureau. I'll kind of get into a little bit of a high-level design of what we're doing in operations. How do you do planned maintenance on a system that you're running 24/7? But the big thing was having the storage capacity, compute capacity to move forward in our modeling. The things that we're looking for is to improve the accuracy of our models, the ability through, typically you think of resolution, how to get those grids smaller, how to better resolve the dynamics. We talk also about being able to run the models more frequently. So if we get into a severe weather situation, you want to be able to start increasing the number of runs. What that really means is, do you have information coming in that allows you to reset the model every hour, every 3 hours, or 4 hours, such that you have new information to provide to people on the ground? So we'll talk about improvements in that area. The next one is more valuable. So if we put out a forecast, how do you know if it's right? If it's a single run, then you really don't have enough information. So that's when the ensemble modeling comes in, and we start looking at how to come up with probabilistic forecasts, something that's going to tell you more about how certain are we of our forecast, where do we think we have problems. So that becomes a really rich set of information. And the last one is then looking at how to be more responsive. So if we have a situation happening, we want to be able to move our models into the area of interest, whether it's a bushfire, flooding, tropical cyclone. And we want these to be high-resolution models that will be able to focus in on the event and provide the people on the ground and the people in the forecast centers, again, with better information. So these are, the blue boxes are what the Bureau typically focuses in on. We look in emergency responses that are minutes to hours. Kind of minute type applications would be emergency environmental response where there's chemical, nuclear, any kind of an event like that where we want to start modeling in the atmosphere, oceans, where that material is going. Looking at hours, if there's a thunderstorm approaching, we want to be able to give you good information about where it's going, where if there's hail in it, if there's lightning. Days, we're looking at preparedness, planning, something's coming up, trying to give a nice forecast with plenty of lead time. The week, months, and seasons are interesting because they're typically a discussion about climate. How things are going to change. Is there a heat wave coming? Are the electrical grids going to be increasing demand? So they want to prepare for that. So there's a number of things that planners, people looking at scenarios would like to see in order to adjust their plans, move their equipment, or change their events or how they respond to something. So those are the applications that the Bureau typically focuses on, and then we work with other partners in Australia to look at things that are years, decades, and centuries. So one of the things that we're doing within numerical prediction is increasing the resolution. So the resolution of our city models are becoming the resolution of our regional models. The resolution of our regional models are becoming the resolution of our global models. And so you just kind of keep seeing this as we have more compute capacity and capability, then we'll keep moving the resolutions up and you kind of see this shift, which is really nice. And this is just to show change in resolution, topography. It really starts getting better information for people on the ground to understand what it means to them. Captures more of the dynamics. Two big areas that we're focusing on is severe weather, high impact weather, so flooding, bushfires, tropical cyclones, where we're driving our resolutions like for tropical cyclones down to 4.5 kilometers in a 5-day forecast. That's going to start in the northwest Australia. And then you'll see that then moving out to other parts of Australia in tropical cyclone impacted areas. What's also nice in that is that we'll start looking at early detection of TC genesis and again trying to give better advance warning of when we see an event that's brewing. The high impact weather modeling, of course, is driving convection scale and will continue to drive that to lower and lower resolutions. But again, the important thing is how we quantify the information, which means going to ensembles and probabilistic forecasting. So those are big investments in the area, and it's a big change. I guess what's interesting about that is it's the cost. It's the cost of computing. It's real time. We call it time critical computing. And that's usually what sets the size of our system. When we look at the climate modeling for multi-week seasonal prediction, that's more opportunistic computing. It's non-time critical. I can run it anytime I want, and it really fills in the gaps in the system. It uses that available capacity. One thing that is true for all of our modeling is we're having to make a decision between deterministic modeling and ensemble modeling. And or change it around. It's increasing resolution or ensembles. So it's how do you use the system and where do you want to put the cost of that. And it's interesting that we are seeing a lot of the need for that certainty of information means that we're going to slow down a little bit on the resolution, and you'll see us doing a lot more ensemble modeling to get that probabilistic, because that's considered by the services to be very important. But when we can increase the resolution, there are benefits to that, and we'll have this kind of tension in the organization where I'll get groups who are going to argue both ways. So in the seasonal, here's a nice improvement going to a 60-kilometer modeling system. This is similar to the Met Office modeling system, where we're now working with the Met Office on the seasonal climate prediction, both on the research and then what we're deploying into operations is is derived off the same system. And what we'll see coming out of this system as well as a 5-kilometer downscaled product. So we're seeing a lot of interest in this, and in terms of multi-week to multi-month products, there's not very many products like this. So this is one of those nice slides that I always like, because it really tells a nice story on a slide, going from the modeling to the services, products, services, and then understanding to the customers what are the benefits of that. And when they start throwing around, $2 billion, $1 billion of, either avoidance of risk or opportune improvements in business, then it does catch people's attention. And this is part of our work is understanding, what is the true value of what we're doing and making sure that's known in government. So we'll continue to work with our business partners, our customers, to understand how we're solving their problems. And we'll see a lot more co-design of information and decision support systems. So one of those things, these systems are only good as the amount of data that goes into them. So observation sets the state of the atmosphere, the ocean. And two nice advances that we're going to be having is the ingest of radar information into the simulation systems and then into the forecast. And that'll kind of give us our more rapid response in forecasting. Himawari 8 and 9 is one of those geosynchronous orbit satellites that is going to give us 10-minute information about what's happening in our area. So between those two products, those will get assimilated in, and that gives us our rapid update and very good information about what's happening in our area, in our region. Lightning Networks is another new product that we're now assimilating into our products, and they'll start showing up in our different products going up on the website. And recently there was an announcement about the lightning data becoming available. So here's our system. It was a CRAE system that $59 million US contract. They've delivered the first part, which is the 1660 teraflop system. And then coming in 2018, we should see an upgrade in that to something over 5 petaflops. I guess one thing to note is that the Bureau doesn't report to the top 500. And it's just the wrong message to the industry, and so you won't see us reporting that. In terms of, just for those of you who like to see numbers about the system and number of nodes, number of cores, aggregate memory, storage, what's interesting about this is how we're doing it. We had the 2015 system delivered. When we get the next hardware, what we'll do is integrate it in with the existing system, and going forward, we'll use both of them. The consideration here is that the life of the system of a piece of hardware should be about 5 years. However, for us to continue on the right technology path, we're looking for upgrades every 3 years. So this is where it'll be an interesting approach to see us keep replacing the 5-year-old hardware with newer hardware and holding on to the older hardware. It does present some problems in procurements, and so I think we'll be working out how to do that going forward, possibly looking at heterogeneous, well, definitely looking at heterogeneous systems integration going forward. So a couple other investments that were made were a system called Terra. It's a small XC40 system. We needed a system that was between NCI and our production system. So we use the NCI reagent system for our research computing, and that was a strategic investment by the Bureau to invest in a collaborative facility. And then within our production facility, it's locked down. So of course we're not going to support or enable more collaborative research computing, or actually no collaborative research computing on our production system. So we needed kind of a system for codes coming off NCI. They need to land on something to be prepared on the Cray system for its architecture to get the code ready before it moves up into our production system. In addition to that, we got a CS400 system for data processing that we integrate with the Australis system, and that's just to focus on some of the data-intensive computing and design the hardware there differently to handle some of the high I/O transaction rates, pre-processing, post-processing that we do with the modeling, and also to give it we treat the file system under Australis as a short-term storage area, and then the storage system under the CS400 is more of a medium-term storage. And so we'll hold the products, the master copy of the products there, and from there we'll send them out to clouds, service clouds, or external customers. Right, and then I talked about the data hosting that we're doing with the Cray systems and the network links. So those were some of the significant infrastructure investments that we made. Just as a quick diagram, NCI research computing, the Terra Platform for in our DevOps pathway, which is a smaller system, but it's the technology is identical to the production, just not as large. And then we get into the Australis platform, we split it into what we call an East and a West, and I'll blame Craig West for that. He named it. And he's sitting here if you want to talk more about what's inside of this. We essentially have production on one half, we have staging, pre-production on the other. However, if we get into a situation where operationally we need to do more computing, we'll take both sides. If we get into planned maintenance, we'll switch the production from one side to the other side. So we utilize all of the computing, and it provides us with the failover capability for either planned or unplanned outages. Same thing as we talk about the CS400s, Aurora. We have the same capability, the same makeup. I didn't try and draw the network diagram or connections as they are, so this is a simplistic representation of it. So the other thing that we did in our work was looking at how to improve delivery. So it was really important that we automate the process, that we have certainty about version control on the software, version control on the binaries. We only have probably about 5 people who touch the production system. Everything's automated to that production system as much as possible. The staging side is where we'll get people who have a need to transition new modeling systems into operations or to perform trials, that they'll get onto the staging half, they'll do what they need to, they'll make sure that they get everything into our Git repository, they'll get them into our suite schedulers, into our version control for binaries using Artifactory. Once we're all happy with that, then we'll proceed to manage it through an automatic deployment process into the production side, whether it's on either side of the system. The other thing that you have to recognize, the way we have these things called suite schedulers. They just control the workflows, but they also control all the interdependencies between the workflows. And so it's a nice sophisticated way for us to manage the business and all the operational runs, all the production runs, from the pre-production of data coming in and the quality control, to the data simulation, to the simulation runs, to the post-processing, and then to any of the data staging out. So we use suite schedulers today. We're using something from ECMWF called SMS, and going forward, we're switching over to something called Silk, which comes out of NEWA. So some of the challenge going forward is the observations coming into the system is increasing. We have HIMO-RE8, which is a 40 times increase. We're getting 1 billion points a day out of that data satellite system. So it starts having an impact on everything we're doing. And worldwide, all the new satellites going up have this immense data capability. And so, it's impacting our networks, it's impacting our data processing, but it is also a great benefit to initializing our models. When we talk about data production coming off the system, we're currently at the APS-2, and the APS-3 is just being delivered into the staging environment, and then we'll see it in production next year. But the APS-3 has a nice big boost, mostly from the ensemble modeling, where we'll go up to about 208 terabytes a day. We'll look at about 23 petabytes a year of data production. That's not data storage, that's just the production. So it means that we're probably not going to save all the data, we're going to have to throw things away. When we get into APS-4, then we see that go up yet again. It was nice, I did the split between deterministic and ensemble modeling so you can kind of see the relative difference. Again, the ensemble modeling always being that much larger, the deterministic being higher resolution, so thus, it's also higher. The ensemble models are usually at 2 times half the resolution, or 2 times the resolution. So it's instead of our deterministic model coming up is, for the global model, is going to be 12 kilometers, but the ensemble model is going to be 30 kilometers. So it helps us to save data and compute, but obviously we're interested in driving that ensemble modeling down to the same resolution as the deterministic model. It's just an affordability issue. So over the years, we see an increasing in temperature forecast skill, rain forecast skill. Essentially, sometimes it feels slow, but this is just the nature of computational upgrades and model upgrades. I've got some other plots where we draw the line with the skill increases, and it corresponds with the compute upgrades. So we're very much tied to our numerical predictions, tied to the computational capability. Ensembles, as you know, we're using it, a lot of information in it, and so there's a lot of interesting applications and work with the customers coming up. Storm detection, getting into artificial intelligence, looking at machine learning. There's a lot of things that we'd like to do that the forecasters are doing today by hand, and so we'll start automating that through machine learning and better data analytic processes. We have been using machine learning-like techniques in the past, and we'll continue to change our techniques and embrace the new techniques and looking for those improvements. Scalability challenges we continue to have. Look at future architectures. We haven't got into GPUs. It's a typical problem. We have a million-line code, and trying to get it all across requires a lot of software engineering. So the Met Office has initiated a project called Alfric that's going to rewrite the codes into both new dynamics, so it's going to be a better globe-conforming grid, but it's also going to abstract away the scientist code from kernels that then we can map into modern processors. So that's kind of the big thing that we're expecting that we're all working on and is targeted for reaching operations by 2024. So we talk about data-intensive infrastructure, new programming paradigms, HPC clouds, containers going forward are those interesting areas. And then very much one of the big areas is software design and engineering. So this was just one of our examples of getting into GPUs using a smaller code and taking a serial code that was running in about 53 minutes and getting it onto basically 8K40s and running it down to 22 seconds. So here's, this is showing Himawari 8, and then that switch was to our model. And so it was just to show that in our modeling, we're corresponding to satellite imagery very well. So this is called synthetic cloud. So we've just gone back to Himawari 8, and now it's gone to our model. You can kind of see a little bit of a difference in the change, but the pattern of the clouds, the movements is the same. So it's a really good example of how we're progressing in our modeling today. Going forward, we're very much looking at improving the resolution for bushfires such as this, where this was a model rundown at 400 meter resolution. Operationally, we can't do that today. This was a research context, but this is operationally where we'd like to go and run those on demand. So thank you very much, and I'll take any questions. Yes. How about down here?
You probably guessed what I'm going to ask. Are you using double precision?
So we are doing double precision. The scientists love it. So there's a lot of work with ECMWF and the Met Office to look at 32-bit and start understanding when we don't really need that resolution. Yeah, so the IFS model from ECMWF, they've recoded it all in 32-bit and shown that there was it was very affordable in terms of the accuracy didn't diverge much from what their 64-bit model runs were, showing that it was feasible. Well, obviously with your method it would be much improved, I could see. Sure. Yeah, but if you look at the methods that we're using for pressure solving, like the IFS model is very much doing Fourier transforms. The Met Office model is more of a finite difference model, finite volume model, and we see a lot of problems either in the conjugate gradient method or in the radiation. So there's a couple different schemes in there that I certainly enjoyed your talk because this, and I wrote back to everyone, oh, here's something new. It's really nice. So we have a big performance gain by going from 64 to 32, and that's what we're looking for. Yes, correct. Yeah. So there's a lot of work. I mean, obviously the Bureau of Meteorology, we also do space weather, we do tides, we do ocean forecasting, we're doing river floods, estuaries, quite a bit of different things. What we haven't gotten into is biogeochemical, but people keep trying to pull us into that, and we'll probably, 10 years from now, that we may be into doing biogeochemical modeling or more biological primary production modeling. I guess it'll be really interesting to see who our partners are and what we can do. Well, if there's some more questions, then thank you very much.